Thank you very much, Jane. Good evening, everyone. I'm delighted and honored to be the first speaker in what promises to be a wonderful program for this year. And the title for my presentation is From Apollo to Desert Storm. And this title actually kind of takes me into a journey through my career of nearly a quarter century of fascination with satellite images or photographs from space. As my colleague and friend Jane mentioned, I am the director of the Center for Remote Sensing at Boston University. And perhaps many people in the room don't really know exactly what this remote sensing is. It is a term that I personally fought for a long time. It is a fancy word for space photography, but we actually did not generate that term. It was generated in the Office of Naval Research. So oceanographers are the ones that actually started it. When we began working with the Apollo program in the very beginnings of it, the oceanographers at the Office of Naval Research had been going over programs for ocean sensing. This is whenever a Navy ship goes out, they have the instruments to measure the temperature, the salinity, and things of the ocean and so on, and that is called ocean sensing. So when they learned about the fact that these bunch of scientists are working with NASA to do imaging of the Earth from space, they said, now we can do our ocean sensing remotely, so it will be remote sensing. NASA engineers heard the term and loved it because it implies magic. So no matter how we actually fought this term, I'm now stuck with it, and I'm stuck with it as a director of the Center for Remote Sensing. However, in the simplest form, remote sensing is really studying something without having to touch it, or investigating a phenomenon from afar, from a distance. So if I go to a medical doctor and he checks my chest with an X-ray machine, he is really using remote sensing technology, because there is a black box that emits the X-rays towards my chest. The X-rays go through the body, and the result is recorded on film. The doctor takes that film, he looks at it, and he explains what is happening to me. And that is really, in the simplest form, that is exactly remote sensing. You depend on an instrument to see through something, whether you can actually see it by the eye or not, and then you take a picture of that and you interpret what you see. So now if we have an instrument that can actually go on the surface of the ground and send rays towards the Earth, and these rays are reflected back, and the reflections are recorded, then I can get the layering or the subsurface layering of the Earth. That is utilizing remote sensing technology. If I take a camera or some other sensor and I put it in a balloon or a kite that looks from that kite or the balloon down towards the Earth and also gives me a picture of that area that it sees, that is remote sensing. And when I take that onto an aircraft or a spacecraft, it's the same thing. Now, as Jane said, I've also kind of emphasized the study of the desert in general, in satellite images. And the reason for that is more cultural than anything else. I am a geologist. I came from Egypt, a country that is 96% desert. And I found that throughout my education, I have really learned very little about deserts. Even though I was educated with first-rate professors in Egypt, and I came here and I studied at the Missouri School of Mines and Metallurgy, part of the University of Missouri system in Rolla, Missouri, and then did my research at MIT in Cambridge, and actually I went to Heidelberg and spent a couple of years there at the Max Planck Institute at the University of Heidelberg, and I thought I rubbed shoulders with some of the finest geologists of our time. And then when it came to really understand what is there in the desert, I realized that we know very little. When I'm studying geology at Ain Shams University in Egypt, I learned everything there is to know about the Himalayas, the Alps, the Grand Canyon, the Paris Basin, the Scottish Diapirs, and the Himalayas, and very little about the desert outside of the classroom. And that bothered me as an Egyptian geologist. And I thought about it, and I found that there are really three very basic reasons for that. For the fact that we know about most other features of the Earth, but not as much about deserts. The first reason is that earth sciences or geology began in England, France, and Germany. And Europe is the only continent on earth that does not have a desert. So the fathers of geology or earth sciences never really had examples of arid landforms to write about. And those who came after them did the same thing, and those who came after them did the same thing, until today. You find a book on geology or geomorphology without a single chapter on arid lands. So that's rather basic. The second reason is the fact that the desert is huge, vast, and the conditions in the desert are also harsh. Very few people would really venture into the desert. If you have a graduate student who wants to pick up a topic for a master's thesis, he's going to want to find some place where you can go to the field, and then after you go to the field, you go down to a bar and have a beer or something and so on, and you're in the desert, there are no bars, there are no hotels, there is no water. Why would you select a place like that to go and study it? The third reason is also more basic to our understanding of the geological profession. We geologists tend to fancy ourselves as people that go into the field, hammer in hand, loaded with a compass so we can figure out exactly where we are out there. And then we go out to the field and we pick up solid rock. And it has to be in situ. That's a Latin term for something in place. So if the rock is not in place, it's worthless. So we go to the field, find some mountain or ledge, and pick up that rock that's in situ. And before you touch it, you have to measure the orientation, so you can mark an arrow on it, the north arrow, and then cut a piece, and then take that piece, go to the lab, make a thin section, look under a microscope, and tell us the history of the Earth. If you go to the desert, there are no rocks in place. What you find is rock rubble, a mixture of rubble and sand, and so those are really very little things for the conventional geologist to see. I came to understand this very clearly when in 1975, well, no, I'm sorry, before 1975, maybe 1973, when NASA decided to cooperate with the Soviet Union in the Apollo-Soyuz test project, and as was assigned to be the principal investigator for Earth observations and photography. And one of my jobs was to bring in the best talent in the country to teach the astronauts about all of the surface features of the Earth. So I did. I brought in the people that will talk about the very cold regions. I talked about the people that talk about the structures of the Earth and the San Andreas Fault and the cracks in the ground and so on. And they had the people that talk about agricultural fields and soils and so on, and got the people that talk about deserts. And there was a very clear distinction between those who spoke to the astronauts about all of these other fields and those who spoke about arid lands. Very little came out. And when the astronauts would ask questions, these people would say, well, we don't know that. And where would these dunes, why would they form these dunes rather than these? Well, we never really found out the reason for that. And so when I realized that our understanding of the desert is hampered by these basic reasons I talked about, I thought perhaps we should utilize satellite images to study the deserts of the Earth. And that is quite possible because of, again, three reasons. The deserts are there because of the lack or scarcity of rain. So they are almost cloud-free. So you can take pictures of them all the time. If you want to take a picture of Orlando, Florida, or the Cape right here, you really have to wait for a while to get some cloud-free environments. But when you are in the middle of the Sahara, you can look down anytime and take a picture. It'll be cloud-free. The second reason is that satellite pictures or pictures from space cover a very large area, so you can actually study regional patterns rather than restrict yourself to one small place, one small region. And the third is that the deserts, because of the lack of rain, have absolutely almost no vegetation. And if you have no vegetation, then the exposed rocks and sands with their colors, the colors are meaningful. So if you really understand the colors or the reasons for the colors of the exposed rocks and sands, then you have almost a soil map, a chemical map of the terrain, if you understand why is this brown color this way or why the reddish color is that way. And you will see some examples of that. But all of these things that we learned about how to interpret satellite images really came from the origins of working with the Apollo missions, or the working for the Apollo missions to the moon, When we, as geologists, when we were asked at the very beginning, maybe about 2 years before the missions, to select or help select the landing sites on the moon. All right, how to do that? We had certain criteria. The place has to be flat, it has to be rock-free or boulder-free, and it has to be scientifically interesting. The only thing we had were pictures taken by unmanned missions, like Ranger, Surveyor, and Lunar Orbiter. So you look at the place and you say, all right, how flat is flat? The flat terrain that we had to select could not be, the inclination could not be more than 12 degrees, because if it's 13 degrees, the spacecraft would topple over. So how do we figure this? Because we had no topographic maps. So we worked on a system of the brightness values. Like we say, if a surface was like this and the sun is like there, then this would be absolutely white. And if it's like this, then it's called complete shadow, so absolutely black. And in between, there are all kinds of ranges of gray. So we measure the range of gray from white to the black, so figure out the tilt of the terrain. All right, we did that. Second is the blockiness of the terrain, because you cannot land in a place where they had very large blocks, because if you do, one of the spacecraft legs would land on these blocks, and also the spacecraft, the LEM, would topple over. So it had to be free of blocks, okay? How are blocks produced on the moon? Well, we thought either by volcanic explosion or meteorite impact. So the farther away you go from the rims of craters, the clearer the terrain, the lack of blocks. Fine, and then scientific interest. Well, it depends then on the interpretation of the terrain. So we learned all of these methodologies during these years. And it really is through this basic study of the surface of the moon that we began to learn the tools of photogeologic interpretation. And what I would like to do this evening is to take you through a journey of these 26 years of fascination with satellite images, from what we have learned about the moon, and then give you an example of this Apollo-Soyuz mission of what we could have done, what we had done using the photographs and observations made by the astronauts. Then we'll move on and show you an example of how we found great rivers in the Sahara, buried under sands, and we found the evidence from shuttle missions. And we'll go through to give you some examples about the correlations we have made between the surface features of the Earth and those of Mars. Get also an example of the application of remote sensing to archaeology, or investigations of a chamber at the base of the Great Pyramid in Egypt. And then we'll end up with what we're doing right now at the Center for Remote Sensing at Boston University, which is to compare satellite images of Kuwait taken before the war and after the war, to see exactly what has changed in the terrain, in the environment, since the Gulf War. So if we start with the slides, please. First slide. And we want to the lights down as much as we can, so that the pictures would look okay.